So our first contributed talk, so yeah, so we're just 2 minutes in advance. So it's Chirag Modi. So can we switch to the Zoom, please? Yes, thanks. So the first is Chirag Modi, who is giving his presentation from the US on CosmicRIM, reconstructing early universe by combining differential simulations with recurrent inference simulations. And so, Chirag, you have 12 minutes plus 3 minutes later of questions.
Thanks. Can you guys hear me?
Yeah. Yes.
Awesome. All right. Hi, I'm Chirag. I'm a Flatiron Research Fellow at CCA, Center for Computational Astrophysics and Math at Flatiron Institute. And I'll talk about CosmicRIM, which was some work we did with Francois Uroge, David Spergel, and Laurence Levasseur earlier this year. So to start with the motivation, our goal here is basically to, given any cosmological survey data, say, for example, if I observe this galaxy field, my goal here is to reconstruct the initial conditions of the universe. By the way, quick question. You guys can see the cursor, right? On the screen?
No, yeah, we see the pointer.
Okay, awesome. Right, so the goal here is to reconstruct the initial conditions of the universe. And before jumping in, you might ask why. And just to keep the scientific motivation short here and focus on the methodology instead, here are some of the reasons. So for example, initial conditions are easier to model analytically. We have been reconstructing BA for about a decade now. This kind of approach allows you to match the data at the level of the field, and so there is no loss of information in principle. We are applying a forward modeling approach here, so that can allow us to do a unified analysis if we want to combine different observables without having to worry about covariances and stuff. But these are only some of the motivations, and I won't go into the detail here. But let's focus on the strategy. So what I want to do here is essentially start with the initial conditions and forward model to the data, write down the posterior for the initial conditions given this data and likelihood, and then maximize this posterior to reconstruct the initial conditions. And the challenge that comes here is that now I'm trying to infer the initial conditions over the entire volume of observed space. And so that can easily go down to 10 to the power 8 density points that I'm interested in reconstructing. And this becomes a high dimensional inference problem, which is generally very hard. I know that this talk focuses on a map reconstruction, which is an optimization problem, while a lot of people in the crowd might be interested in sampling methods like HMC for this. But I would argue that HMC faces similar challenges in high dimensions. And generally, the talk focuses on the methodology of learning optimization schemes, which is more generally applicable than this particular reconstruction framework here. So I hope this talk will be useful for more people than just a niche topic. All right. So to set up what exactly do I mean by hard, let's go back to a toy problem. Say that I'm observing a 3D dark matter field as my data, and my forward model is a simple 5-step particle mesh forward model. So I know the model exactly which generated that data. Say I have only a 64 cube mesh, so I'm on low resolution. So my dimensions are still high, but not as high as a survey, actual legit survey will be. And say the data has only a simple Gaussian noise, in which case I know the likelihood exactly, and I can write down the posterior of my observed data exactly. So here I know all the ingredients of this model, and say I want to do a reconstruction. So this is what I begin with on the right. What I'm showing on the bottom panel here are the true initial conditions and the true observed data here. And say start with a white noise, which is basically just a random white noise field for the initial conditions, and this is the corresponding final field. We'll be looking at the cross correlation and transfer function as the metric. So in blue, I'll be showing the cross correlation between the initial conditions, the linear field, and in orange will be similarly for the similar metrics for the final field, right? So if you take this posterior and just throw it in your favorite optimization scheme, this is what you end up reconstructing. And you see that on the large scales, you are missing all the powers. On small scales, you have more power than you want. And the cross correlation is poor all over, even on the largest scales. So what could be going wrong? And the reason primarily is twofold, we believe. The The first is the volume effect, that it's a high dimensional problem, and most of the volume is concentrated on the small scales because we have way more small scales than we have the large scales. And so the optimizer basically spends a lot of time in optimizing the small scale modes, but is not able to get it right because we have nonlinear couplings in our forward model. We know that information in gravitational evolution goes from large scale to small scales, and so you can never hope to get small scales right if you don't get the large scales right first. So what we can do for this is come up with an ad hoc annealing or adiabatic optimization scheme and say, what if I smooth my residual, this term, on the small scales first? And what this will allow you to do is to like force the reconstruction on the large scales, because the small scales will be suppressed by this prior term here. And in that case, you're focusing on the large scales first. So say if I'm smoothing on 2 grid cells, this is what I get. I can then successively reduce the smoothing. So say if I reduce the smoothing to get 1 grid cell, I go further in my reconstruction, and then I can reduce the smoothing altogether. And this is what I converge to, which looks very much close to the truth. These scales were anyways noise dominated, so we didn't hope to reconstruct them in the first places. And this seems to be the best we can do, which is pretty good, if you ask me. But then the question arises is that what if we did not have this intuition to come up with the ad hoc annealing scheme that we came up with? What do we do in that case? Say if I'm not observing dark matter, but some other observable where I do not have this intuition. So to motivate that, let's take a step back and let's look what the optimization scheme is, what's happening here in the first place. So what I'm doing here is I want to do an inference where I have a likelihood of some p for a given data. I have some parameters x that I'm interested in, which is the initial conditions, and I have a prior Gaussian. And what I did was write down the posterior for that. So this is the joint probability. And if your evidence of the data does not depend on the parameters, then maximizing the posterior is same as maximizing this joint. And in the simplest case, what you can do is like a gradient descent algorithm to optimize this, in which case, so gradient descent is inherently an iterative algorithm. And what you do at every time step, at every iterant, is essentially you take your proposal x, you calculate the gradient of your likelihood term and the prior term, you pass them through a function, which in the gradient descent case simply multiplies it with a step size epsilon and predicts you the next update point. And you just throw that back into the likelihood in the prior box and keep on repeating this iteration, right? If you think about more sophisticated algorithms that perform better than this, they essentially modify the update equation here. For example, momentum methods keep a memory of the past update, or Gauss-Newton LBFGS use higher order Hessian information in this case. So that motivates CosmicRIM, and what we now want to do is essentially learn this high dimensional inference problem, like how to do updates here. And the strategy is to combine essentially differentiable cosmological simulations like FlowPM, which give us the gradient for this forward model, with learned optimization scheme. So the one that we ended up using here is called Recurrent Inference Machine RIM, which was first proposed in this paper. And what it does is essentially uses a recurrent neural network, which has 2 functions, h and g. And these 2 functions essentially try to learn the update equation at any time t. And since it's a recurrent neural network, it also has a hidden state s, which can keep a memory of the past updates it has seen. So at every time, every iteration, we are solving these 2 equations. So we first take a function h, which takes in the current hidden state, the current gradient to the joints, and the current position that we have, current proposal that we have, and updates the hidden state equation. And then we take the function g, which basically takes the current state, the same gradients to the joint, and updated state equation to predict the next point that we want to propose. Unfolded, it looks like this. So you start with some point x0, you calculate the gradient, pass it through the recurrent, these are the functions h and g, which basically give you the next updated point as well as the next updated state. At the next update point, you again calculate the gradient, pass these 3 things to the function, and so on and so forth. To train this scheme, to train these recurrent networks, at every time step, you can compare the prediction that you have with the true answer that you are seeking. And in our case, we ended up simply write down the loss function as the L2 loss between these 2 updates and the true solution. You can play games like weighting this so that like you are weighting more the later iterations than the first iterations. But in our experiments, we found that just equally weighting all of them performed the best. Right. So the paper that proposed REM essentially was trying to solve a linear problem in fairly low number of dimensions, and our challenge is slightly different. We have a nonlinear problem in higher dimensions, so we made some modifications to the architecture. The first modification was we used UNet instead of just fully connected networks. The motivation here is that we know fundamentally in cosmology for our problem, the large and the small scales, we have a clear separation on those scales. So we use effectively two REMs, essentially one to learn the large scale and one to learn the small scale optimization. And secondly, instead of passing in the gradient information at every time step to the REM, we pass what an optimization algorithm like ADAM would have predicted in this case. What would be the update predicted by the ADAM algorithm? This turned out to be crucial, and it kind of makes sense because we know that the gradient descent fails completely for our problem, while ADAM is able to get somewhat close to the correct neighborhood. And so for a nonlinear problem like this, this was one of the important points to keep in mind. All right, so we ran some experiments. The results that I'm showing here are for mass-weighted halo as my data, number density 10 to the power minus 3 in a 400 box. My forward model is 64 cube, 2 LPD dynamics with second order bias model. And this is what the results look like. So this is, again, I'm showing cross correlation and transfer function between the true initial conditions and the reconstructed initial conditions. The results for REM are shown in the solid lines, so the orange and the blue. And the best reconstruction we had for earlier for LBFGS with 400 times iterations is shown in the dashed lines here. And we see that REM is able to do in 10 steps what it takes over 400 steps for LBFGS, and the transfer function is more stable. You can improve the performance of REM by, instead of starting from white noise, you can start with more informed initial conditions, more informed guess. So like, for example, I can throw in the standard reconstruction input. You cannot do the same thing for the annealing scheme because the first step of annealing scheme is to smooth everything. So you basically start from zero in that case. You can open the box and see what REM actually learned. So if you plot all the 10 steps of the REM proposal and the cross correlation, you see that it effectively ended up learning what we were trying to physically impose, that it first reconstructs the large scales and then pushes to smaller scales slowly. And the other thing it learned was a local minima, so that if we start from the output of REM, we can run other optimization schemes after from that particular point, and we found that it didn't really improve the results. So it really did learn a local minima in some sense. All right, here are my takeaways, and since I'm out of time, I'll just leave them on the slide and take questions.
Thank you very much, Chirag. Any questions in the room or remotely? Awesome.
A comment and a question. So my comment is, why don't you look into this metric Gaussian variation inference scheme I presented yesterday? That might be very suitable for your kind of problems. And my question is, so what is the loss function you use in order to train G and H, so the predictor for the next step?
So can I share my slides again? So firstly, thank you for the comment. I'm actually looking into that paper right now. It's open on one of my other screens. So, and I think it can be useful. So thank you for that. And to answer the question, the loss function is essentially this. At every time step, we are just, so what we essentially for training, what we do is run the REM for like all the 10 steps and get all the 10 updates that it has predicted. And then we're just comparing all those 10 updates with the true solution, because in simulations, we know what the true solution is, what the correct answer, true initial conditions are. So we're just comparing all of them with the truth at the level of L2 loss and adding all of them up.
Thank you, Chirag. Another question? checking online. No? Well, maybe then we can proceed to the next speaker. So thank you, Chirag, again. And